Okay, so this is the 2022 to 2023 test 2. And I figured I would work it for you guys and see if that is helpful for you. If not, I don't have to do these videos, but I assume that some of you will find this useful. Okay, so I'm going to zoom in. You have a copy of this thing somewhere on Canvas of this project, so you can work it there if you want. Okay, the brakes are applied to a moving vehicle, so we got some kind of moving vehicle. You don't have to draw a picture, of course, causing it to uniformly slow down, so its speed is going to get less and less and less until it comes to a stop. While slowing, it moves a distance of 40.0 meters, and over a time of 8.15 seconds to a final velocity. Oh, it doesn't quite stop. Okay, so its final velocity right here, this last little thing, is 1.40 meters per second, at which point the brakes are released. All right, so let's get this into kind of symbolic form. So here we go. We got givens. The final velocity is 1.40 meters per second. The displacement over that time is 40.0 meters. And the time is 8.15 seconds. Okay, and then what are we looking for? We're looking for V naught. Okay, so this one's a little bit interesting, I think, only because it's not really because it's going to require two equations, so we're looking for V naught, and V naught shows up all over our equations. We've got a V bar equals delta X on delta T, and you could imagine there's a V naught in there somewhere. In fact, that V naught comes out here, V naught plus V on 2. We also have this equation, V equals V naught plus AT. We've also got delta X equals V naught T plus 1/2 A. Sorry, the kind of program closed on me for a second there. Let's see, V naught T plus 1/2 AT squared. And then of course we've got, my favorite one, V squared equals V naught squared plus 2A delta X. There's a problem with almost every single one of these equations for this one. Let's see. So there's a V naught right here. But we could use that equation, but all that's going to do is get me V bar, right? So there's a built-in V naught here, and it actually comes in this form right here. Okay, and this is exactly how we're going to solve it, is combining those two. But I want to show why the other three equations are no good. And it really boils down to the fact that, sure, each one of those has a V naught in it, but it also has acceleration. Okay, and we do not have acceleration. And in fact, the second part of this problem, we're going to ask for acceleration. So, but there's a reason why we can't just use those to get acceleration right now, which is we don't know V naught. Okay, so what I'm going to do here is right off the bat, I'm going to make use of the fact that V naught is in this equation, but I know everything in this equation to give me V bar. Okay, so let's start with V bar. So V bar equals delta X over delta T. I'm running out of space here, so I'm going to go ahead and rewrite that. I don't like to work sideways, but I don't really have a lot of space here to do this another way. So let's see. Come on, you can do it. V bar equals to delta X, which was, 40 meters? 40.0 meters divided by the delta T, which was 8.15 seconds. 8.15 seconds. So V bar equals... Okay, I'm getting 4.907 or 080 meters per second. Okay, where, I know that my final answer is going to have 3 sig figs, so we're going to keep 5 throughout the problem. Okay, to make sure that we don't have any rounding errors. Okay, cool. So that's a really ugly written, but that's 4.9080. Okay, so once we have that, then I can use this equation right here because of everything that I need in order to get the initial velocity. So I can go up to that equation. I can say, okay, cool, v bar equals v naught plus v over 2. I'm going to rearrange this. I'm going to multiply the 2 up. 2v bar equals v naught plus v. And so now I'm going to rearrange that again. I'm going to say v naught equals 2v bar minus v. Okay, the units work on that because, I've got a meters per second or length per time, length per time, length per time. So I'm going to be good. Okay. All right, so to solve for v naught, I'm going to do 2 times v bar, which is 4.9080. And I'll just kind of leave that in my calculator. And that'll, I already have that in my calculator from the last step, so I don't even need to worry about any rounding there. Minus the final velocity, which was 1.40. We know it from right here or right here. So we'll go over here, we'll go 1.40 meters per second. Okay, so the initial velocity then is, 8.4159, or really, I guess it's 60. Okay, now because this is a test, we're going to want that in 3 sig figs. So the answer we're going to box off is 8.42 meters per second. Okay, we will keep this number right here for the next step should we need that information, right? Because we want to keep 5 sig figs as we work through, right? But this is the answer that the test is asking for. All right, so in the next step, okay. So basically, now I could take all of my givens and just bring them down here. I mean, there's no reason to do that. But we know one more thing, which is that we know V naught is 8.4160. Okay, meters per second. Oh, the last thing we should do before we get out of here, is this reasonable? Reasonable. And I would say it seems like it. So if we end up at 1.40 meters per second, and we were slowing down for 8 seconds at, what was our, we don't know our acceleration yet. Well, anyway, we know we were slowing for 8 seconds. So it had to be a larger number than the 1.40. I'm okay with it generally. I mean, it's hard for me to, just kind of picture this off the top of my head. But it was key that if we ended it at 1.40 meters per second, we had to start at something faster than that because we were slowing down, right? So that's about as close as we can get, really. Okay, so what is acceleration in meters per second squared while the brakes were being applied? Assume the initial direction of motion is the positive direction. Okay, so that last little bit, assuming the initial direction of motion is the positive direction, leads me towards this equation because those squareds make it hard to figure out if your answer is going to be positive or negative. I think in this particular case, you could use almost any equation, any of these equations that you wanted up here. I guess it's telling you kind of the signs on all of them. That might be the easiest one to work with. It looks to me like on my key, I used the squared equation, but I think you probably could have used just about anything you wanted here. I don't particularly like using this one. Just because solving for A there is going to be a little bit nasty. Let's go ahead and use this one. We'll go kind of a slightly different route than my key. And we'll say V equals V naught plus AT. We're solving for acceleration, so I'm going to bring the V naught over, AT, and then I'll divide by time. So acceleration equals V minus V naught over time. So the acceleration equals, we're just going to plug in at this point. V is 1.40 meters per second minus V naught. Where's V naught? Right here. So, sorry, it's right here. All right, we want to keep all our sig figs. 8.4160 meters per second, and I'm going to divide by the time, which was 8.15 seconds. Okay, notice we're going to get a negative number here. And I'm getting negative 0.86085 meters per second squared. Notice I've got meters per second divided by seconds. So that's going to be meters per second squared, which is what we want. And I want 3 sig figs. So we're going to make that negative 0.861 meters per second squared. Okay, so I feel pretty good about that. It's certainly a reasonable number. It had to come out negative. right? Because we were slowing down. And we were assuming that we're going in the positive direction. Okay, on to the next one. A ball is thrown vertically upward with a speed of 13 meters per second. That's not a lot to go on. In fact, I wonder what all this space is all about right here. Let's go ahead and just give it a given. So V naught equals, I'm going to call that a positive 13.0 meters per second. I want to know how high does it rise. Okay, that's a challenging question because it seems like we have almost nothing to go on. So what we're going to do here is I'm going to go back up to givens, and I'm going to note that the acceleration is negative 9.81 meters per second squared. That is a given because this is a free fall problem. A and B have to do with when it gets to the very top of its flight. So for both of those, the final velocity is 0. Right, what about C? How long does the ball take to hit the ground? Okay, so this only applies to A and B. A and B. Okay, so what do we want? So here, for required, I want to know delta y at the top. I don't know how to call that. Maybe I'll call that delta y top. Not really sure what to call it. We'll call it delta y at the top. Okay. So my inclination here, I'm not sure if this is there's always a lot of different ways to solve this. So I want to solve this. I'm going to use this equation. V squared equals V naught squared plus 2a delta y. If I'm going for the top, that means that this guy right here, the final velocity is going to be 0. Okay. I'm going to go ahead and keep it in the equation just for now, just so we'll have a more general equation, but we'll get there. So we're going to solve for delta y right here. So if I rearrange that, I'm going to get v squared minus v naught squared equals 2a delta y. And then I guess we'll divide by 2a, right? So let's go over here. So I really didn't provide this particular class enough space for this. Or maybe it's because this marker, really likes to create huge spots. So v squared minus v naught squared over 2a. Okay, so now that we're going to make this specific to the top location, the final velocity at the top is 0. So now my equation is delta y at the top equals negative v naught squared divided by 2a. Okay, so delta y at the top equals negative, what was my initial velocity? 13 meters per second squared, 13.0 meters per second. Okay, we're going to square that. We divide that by 2 by negative 9.81 meters per second squared. Note that negative sign right there is not inside that square. Okay, so it's not going to go away, which is fortunate because we have a negative sign underneath it, and we hope that we're going to get a positive delta y because it did in fact go upwards. And man, we were getting a lot of the delta y at the top. We were getting a lot of 861s here. 8.6137 meters. Now again, we were expecting meters. We got meters. We've got 3 sig figs, so we should keep 5 throughout our problem. So delta y top for reporting purposes, 8.61 meters. Okay, but this is the one that we're going to use in this step should we need it. Okay, so this second bit, we want to know how long does it take to reach its highest point. We could use this this value right here. There's a few different ways we could use that value if we wanted to. For example, and I'll do this in red, but we could do delta y equals v naught t plus 1/2 a t squared, because if we were looking for time, we know this is what we're looking for. We know the acceleration, we know the initial velocity, and now we know delta y because we just solved for it here. The problem with this is that's a quadratic, and while a quadratic is something that you can solve and you have to know how to solve, nobody wants to do that if they can avoid it, right? So the easier way to do this, and this is nice, so as these problems work and you solve for more information at each location, you get more and more options for the way to solve it. So in this particular case, I'm going to recommend v equals v naught plus at. Again, I mean, it's very similar to the other equation, to this equation right here. We're looking for t. We have the acceleration, we have the initial velocity, we have the final velocity. So let's go ahead and rearrange this for the time. So first I'll do v minus v naught equals at, and then I'm going to divide both sides by a, and we get t equals v minus v naught over a. Okay, I really need to zoom in so that this, so I can write a little, smaller. Anyway, so the final velocity at the top is 0. The initial velocity was 13.0 meters per second, and the acceleration was negative 9.81 meters per second squared. Okay, so the time should be relatively quick. Okay, so over here, I'll just say t equals 1.3252 seconds, 3 sig figs, t equals 1.33 seconds. Which seems about right? If it's going upwards at 13 meters per second, and it's losing, 13 meters per second, and it's losing essentially 10 meters per second every second, you would expect it to take a little over a second for it to come to a full stop. Okay, so far so good. It looks like that's how I did it on my key, so that's nice. Okay, how long does the ball take to hit the ground after it reaches its highest point? Let's see here. Okay, so in this case, this is a really easy problem because we can use symmetry. So if you wanted to, you could do essentially no work at all for this one. You could just go, okay, well, we're just going to copy this answer down. It was just as far up as it is down. So we could say t equals 1.33 seconds by symmetry. Okay, now I want you to be careful if you use symmetry. Okay, remember that means it has to be the same distance up as down, right? Because if it was asking for how long does it take to hit the ground, and the ground were lower or something interesting like that, then you can't really do that. If you wanted to solve this otherwise, what I would recommend is kind of a whole nother given. So in this case, we'd be talking about from the ball's at the top, where its initial velocity is 0, and it'd be falling right back down to the bottom. And we would know that its acceleration was negative 9.81 meters per second squared. And we would know what its delta y was because we solved for that. Where was that? We solved for that right here, 8.6137. 8.6137 meters. Okay, and once you have all of that information, you can solve for the time. Now this is a little bit, trickier because if we're looking for time, okay, this one I think we're not going to get away without using the quadratic equation. This is solving. We're making no assumption of symmetry, right? Because some of you are looking at it right now, and you're wondering, well, why don't we just put v equals negative? What was the final velocity? What was the negative 13 meters per second? Negative 13 meters per second. And the reason for that is because that is an assumption of symmetry, right? If I knew symmetry, I could have just written that answer, okay? But because I don't know symmetry, because I'm assuming I don't know symmetry, because I'm just going to assume that I can't do this particular thing, and for some reason my eraser doesn't want to erase that. Okay, so if you don't assume symmetry, then what we have to do is we have to say, okay, well, delta v equals v naught t plus 1/2 at squared. And this is a little bit obnoxious because, we're not working in x, so we'll turn that into a y. Okay, delta y. Okay, I do need a note. Did you catch my error? Did you catch my error? Looks like I had the same error on the key. That's interesting. Well, kind of. But anyway, so there should be a negative sign right here. Okay. All right, so I'm going to rearrange this. Let's see. So I'm going to bring the delta y over here. And I'll write this as 1/2 at squared plus v naught t minus delta y equals 0. Oh, no, wait, we're not going to have to use the quadratic formula. Well, there was always a possibility, but I guess it didn't happen this time. Okay. So anyway, so my rearranging there might have been a little bit unnecessary. And the reason this becomes unnecessary is because the initial velocity is 0, so this term goes away. So if that term goes away, then we're solving for time here, right? So we're solving for time. So so I'm going to undo the work that I just did. So I'm going to bring this back over to the other side. So I'll say delta y is on the other side equals 1/2 at squared. So now I'm going to multiply both sides by 2 delta y, and I'm going to divide by a. I'm going to take the square root. T equals that. Okay. And that's a little bit gross, but not it's a lot better than a quadratic formula. So let's go ahead and do it. So the square root of 2, what's delta y? Oh, negative 8.6137 meters divided by negative 9.81 meters per second squared. Again, notice like using those negative signs worked out really nice to our advantage, because here we are, and we're going to end up with a positive sign underneath that radical. So let's see here. Okay, so my calculator says, and this is going to be positive or negative, so that's always an important potentiality, 1.3252 seconds. We're going to throw out the negative because that's actually going backwards in time to when it was thrown. And we'll use the positive, and we'll use 3 sig figs. So t equals 1.33 seconds, which we knew by symmetry, but it was still nice to to affirm. Okay, so that is the first test on this particular group of tests. Okay, and it looks like I agreed with my key, which is always nice, because sometimes there are errors on the keys. So I feel pretty good about that I did not end up with that. Oh, the helicopter problem. We did this one in class. Okay, so this is the second version. I don't necessarily know which class or got which, but that is okay. Okay, a small mailbag. I think this is interesting. Okay, I think the key is slightly out of order. So if you're looking at the key to try to follow along with the work from the key, I'm assuming this means that the key is out of order. Let's see here. Baseball is hit, so it travels straight upwards. Yes, it's just out of order. So don't be frightened. It's just out of order. Okay, so if you're looking for this, just scroll around. You'll find the key. Okay, a small mailbag is released from a helicopter that is descending steadily at 2.95 meters per second. So I'm going to kind of draw the helicopter as a dot, just because that makes my life easier. And I'm going to draw the mailbags also as a dot. Okay. The mailbag is in the helicopter. So the mailbag has an initial velocity of negative 2.95 meters per second. And the helicopter is a little bit interesting because it has an initial velocity of the same thing, but that's also its final velocity and its average velocity, because it's not speeding up or slowing down, negative 2.95 meters per second. I like to make note of the fact that all of these things are true, just because it means I can plug it in anywhere in those equations that I like. Okay. The other thing to note here is, I guess we were going to kind of do a red thing here. So acceleration equals negative 9.81 meters per second squared. Acceleration for the helicopter is non-existent, right? It's acceleration equals 0. In fact, that's why those things are true. Okay. We do also know that the time for both of them is 5.00 seconds, because if you guys remember this problem, they're going to ask for how far apart the helicopter is from the bag, 5.00 seconds. Okay, after 5 seconds, what is the speed of the mailbag? Okay, this is not a terribly difficult problem. I guess these are the givens. What do we want to know? We want to know the velocity equals what? Okay, so the solution here, the nice thing about this one is this one lines up straight ahead with v equals v naught plus at. So let's go ahead and solve that. So I don't even need to rearrange it, which is always nice. Negative 2.95 meters per second. The whole point of this problem is to make sure you recognize that if something's being dropped and it already has a velocity, that it's going to start at whatever that velocity might be. It might be 0. It's usually 0, but in this case, it is not. Okay, plus the acceleration, negative 9.81 meters per second squared. Let's zoom in so it's a little bit more visible. And the time is 5.00 seconds. So we're going to want 3 sig figs. So I'm going to go ahead and solve it. And then, we're going to keep 5 just in case we need it for the next one. Okay, so the calculator comes out to a nice clean 52.000 if I want 5 sig figs meters per second, but really your answer should be 52.0 meters per second, right? Okay, so we know that final answer is going to have 3, so we're going to report 3, but we're going to keep 5 throughout our problem. Okay, how far is it below the helicopter? So to get that, we need the position of both the helicopter and the mailbag. Okay, so this is a great question. I love this question. So the position of the bag, which looks like I'm doing this in color, maybe I'll just make it a B so that so that we don't, in case you're colorblind or something. I mean, it's much more common in men than women, so I'm told. V naught of the bag times time plus 1/2 AT squared. Okay, straightforward. And then delta Y of the helicopter equals V naught of the helicopter times time plus 1/2 AT squared. Now we're going to note right off the bat that this term right here is going to go away because the helicopter is not accelerating. Okay, so that makes our lives a lot easier. The other thing that we should note, because we want to know how far it is below the helicopter, we can note that this term right here and this term right here, if we subtract them, that term is going to go away. So our final answer is going to be this thing right here, 1/2 AT squared. And we'll prove that in a second, but we'll just go ahead and keep working. Okay, so delta Y of the bag equals V naught, which is negative 2.95 meters per second, times the time, which is 5.00 seconds, plus 1/2 of negative 9.81 meters per second squared, times this time squared, which is 5.00 seconds squared. Okay, delta YB of the bag this better be a negative number, right? Because it's going downwards. So it's pretty far down there. It's a negative 137.375, we'll say 38 meters. Okay, that's pretty far down there, okay, from where it was released. But the helicopter kept going down as well, and unfortunately I worked into the helicopter space. So we'll kind of slide over a little bit. Delta Y of the helicopter equals negative 2.95 meters per second times the time, which is 5.00 seconds. So delta Y of the helicopter is, I'm getting negative 14.75. Technically, there should be a 0 there if we're keeping 5 sig figs. Although I guess for the keeping, you don't even necessarily need to write the extra ones, right? So if we want to know the difference of the two, like how far apart they are, so let's see, what would we call that? I don't know what we would call that. We would call that the distance. Maybe we could say distance between them is the position of one, delta YB minus, sorry, this is silly. Okay, sorry about all this clicking. It's the position of one minus the position of the other, right? Okay, so the distance is negative 137.38 meters minus negative 14.750 meters. Okay, so the distance between them is, and we'll take an absolute value because it just said how far is it below the helicopter. They didn't really want a number on this particular problem. So let's see. Okay, so I'm getting negative 122.63. So we'll make that positive 122.63 meters, or we could just say the distance is 123 meters because we want 3 sig figs. Is that reasonable? I mean, it's hard for me to picture it. I guess something was falling for 5 seconds. The helicopter's moving, but not very much. So could I imagine it getting 140 meters? Sure. I don't see any reason why not. Okay, looking on my key, there's a shortcut to this one. And the shortcut is pretty interesting. I don't even remember coming up with this. But basically, is to move your reference frame. So make a new reference frame, right? Instead of thinking about everything as pertains to an observer who's somewhere else, let's make the whole problem in reference to the helicopter. So here's the helicopter, right? Okay, and you know, the bag relative to you, because you're going downwards relative to the Earth. Relative to the Earth, you're going downwards at 2.95 meters per second. But relative to you, the helicopter is going down at whatever this speed is, right? So it's at its acceleration times its time. The initial velocity doesn't matter because you gave it that, right? So the final velocity for the bag relative to you is v equals at. Okay, is 49.05 meters per second. So if you use that as your velocity relative to the helicopter, which works out because what we want to know at the end is what's the distance for this thing relative to the helicopter. So in that case, we could say, well, v equals v naught plus 2a delta y. So this delta y is relative to the helicopter, this v naught is relative to the helicopter, this v is relative to the helicopter. Okay, so so all of that is nice and clean. So relative to the helicopter, the initial velocity of the bag is 0. Okay, relative to the helicopter, the final velocity of the bag, it's moving away at 49.05 meters per second away from the helicopter. And then plus 2, oh, that's not a 2, 2 times negative 9.81 meters per second squared. And then we'll solve for delta y. Okay, and if you do the math here, you get a nice pretty 122.625 negative. And if we round that, we get delta y equals negative 123 meters, which is pretty stinking nice, okay? Although it looks like in my key, I left those as positive. Oh, right, I know why this positive. It's because we wanted to know how far below. So I might say, well, the distance is 123 meters, right? Okay, so cool. All right, so that's an alternate way. I don't expect you to pick up on the alternate way. Okay, let's see here. Two boats start together and race across a 54-kilometer, we did this one in class too, 54-kilometer lake and back. So here's my lake. Okay, 54 kilometers. Boat A goes across at 54 kilometers per hour and returns at 54 kilometers per hour. So this is boat A. And that was 54 kilometers per hour. Boat B goes across at 27 kilometers per hour. This is B, and comes back at 81 kilometers per hour. Turnaround times are negligible. Boat completes the first round trip wins. Which boat wins and by how much? Okay, we remember this from class, and of course I told you guys I hate this question of by how much. If I were to do this again, I would hope I would remember to say how much time or how much distance, right? We'll go ahead and do both. Okay, so technically most of you guys will remember from class that boat A wins, but let's go ahead and figure out the time for boat A. Okay, so for each. So for boat A, well, I gave all my givens up there. I'm just going to go ahead and solve this one right here. Okay, so for boat A, I need to get the time on the way there plus the time on the way back. 2. Dadgummit. That's so annoying. Okay. T2A. Okay, so the time there and the time back. Okay, let's say T for boat A is that. T for boat B equals the time for the way there for boat B plus the time for the way back for boat B to B. Right, now the key here, of course, is that the times are related. So these boats are going constant speeds on the way there and constant speeds on the way back. So we can use this equation, V bar equals delta X on delta T. Okay, so let's rearrange these, and I could say the time equals the displacement divided by the velocity. Okay, so for boat A, I can say that this is delta X1 divided by, V bar 1A, I guess. Yeah, so boat 1 in direction, or boat A in direction 1. Okay, and then you will use this equation again right here. So we're just going to basically plug this equation in for all of these things, keeping in mind the distance and the boat, right? So this one will be delta X2 over V bar, direction to boat A, right? And so for the boat B, we'll go TB equals delta x1 over v bar 1a plus delta x2 over v bar 2b. Sorry, that should be a b, shouldn't it? You know, 1b. Okay. So I'm just going to kind of keep on rolling down here. And most of you guys can do this particular one in your head. So we're going to go plus, what was it, 54 kilometers? 54 kilometers divided by V1A is right here, plus 54 kilometers per hour. Okay, plus, and then delta x2, that's coming back across the boat, so it'll be a negative 54 kilometers divided by that velocity, which is negative 54 kilometers per hour when we're coming back. Okay, we'll go ahead and solve that. So TA equals, this is 1, 54 divided by 54, and our units are hours. Plus, same thing on the way back, except the negative sides cancel. So TA is 2 hours. Sweet. Okay, so TB equals 54 kilometers plus negative 54 kilometers. Okay, and then this would be 27 kilometers per hour. This would be negative 81 kilometers per hour. I think if I gave this problem again ever, I would give more interesting numbers that would make it seem like a real race and something that you couldn't necessarily just, you know, kind of think about in your head. Okay, so this is going to be 2 hours, and this is going to be, I guess that's 2/3 of an hour, so 2 hours and 40 minutes. So TB equals 240. I'm not really sure how to do this in sig figs. I don't even know if that officially counts as units. I kind of think it does, but it's kind of unclear if those are hours or minutes. You know, I'm going to be I'm going to be reasonable on that if that happens. So one thing you could do here is you could say, okay, well, boat A wins by 40 minutes. Okay, so boat A wins. Okay, so that's you know, a good answer. However, it wanted to know by how much. So the way you'd figure that out is you see, well, boat B is behind. Let's suppose it wanted it in distance. Well, then you would say, okay, you know, I haven't made the test yet for this year, so who knows? But you might say, okay, we got for this 40-minute number, we need to apply that 40 minutes to the, you know, to boat B. How far back is boat B when that happens? So what we would do is we'd say, okay, well, boat B, assuming we don't know that, you know, this 2 hours and that 2 hours are identical, right? So we know where boat B is at the end of those 2 hours. It's just reached the far shore. But let's imagine that we didn't. So we would take this 40 minutes, and I would say, well, V bar equals delta X on delta T. So what I want to know is in 40 minutes, how far back is the boat, right? What, you know, how far does it still have to come? So what I would do is I'd say, okay, well, delta X equals V bar delta T. Let's see, and so how fast is it traveling during that time? On the way back, it's traveling at 81 kilometers per hour. Okay, so it's 81 kilometers per hour. So I'm gonna want my units, that delta T there, I'm gonna want that to be in hours, so I'll make that 2/3 of an hour, right? And that's gonna be equal to delta X. And I'll switch back to blue. I don't know why it was red right there anyway. So delta X is gonna equal, 2/3 of 81 is, well, I should know this from just above, but it should be 54, right? 27, 20, yeah, that's right. Okay, 54 kilometers back. Okay, cool. All right, sweet. What is the average velocity of the winning boat? Okay, this is a trick question. I hate these, but they show up all the time. We have to remember that if it's asking for average velocity, so let's see here, V bar equals delta X over delta T. The temptation here, of course, is to go, well, he went 54 across and he came back in 54. So so the temptation is just write down 54 kilometers per hour right off the bat, because he was always going 54 kilometers per hour. The other temptation is to go, if I were to actually calculate it, as I would say delta X, he went a total of 180 kilometers. And he did that over, what, 2 hours? Yes, 2 hours. 2 hours, and if you do that math, you get 54 kilometers per hour. Kilometers. I can't write. Guess I've been working on this for 40 minutes now, so it's not completely surprising. V bar equals 54 kilometers per hour. Okay, both of these would be wrong. Okay, because this is the trick question. Remember, velocity is a vector, and it is the displacement over the time. So V bar is the displacement over time. So the displacement in this case is he went back to where he started. So his final total displacement is 0. Doesn't matter what the time is, although the fact that it's 2 hours, you could put it down there if you wanted. But the V bar is 0, and it doesn't even need units. Okay, so I can't believe I put that on a test. How much did I make it worth? I don't know how much I made it worth. I hope I made it worth like 2 points, right? Because obviously this is where all the work was. This is a fairly easy problem to make it onto a test. Oh yeah, it looks like I put a little +2 down there. Yeah, because I don't like these trick questions. Okay, anyway, ooh, multiple choice, eh? Yeah, this was before I learned that I could just use Scantrons, right? Which are much more reliable than me grading by hand. Okay, so let's go to this next one. This tortoise problem, is it a tortoise problem? Oh no, so at the back here, there's a tortoise problem. This is an honors problem. I don't think I would make you guys work this one. So maybe, I mean, I hate to say it's an honors problem because anything could happen. I don't want to tell you like don't ever learn this problem. I think, I don't know, you guys could do it. Anyway, we'll get there in a second. All right, so a baseball is hit so it travels straight upwards after being struck by the bat. A fan observes that it takes 3.10 seconds for the ball to reach its maximum height. Okay, cool. We're at another maximum height problem. Things love these maximum height problems. You should know that I don't make these problems up, right? Okay, so given, what do we know? Given, we know time is 3.10 seconds for the ball to reach its maximum height. As soon as you see your maximum height, that means not y. That means delta, dadgummit. That means v equals 0. So the final velocity at the top is 0. And always in free fall problems, it's helpful to write down the acceleration because sometimes, like in this problem, it's like all of these. They gave you one number, but really they gave you 3 numbers, but there was only one number written. And so, if it's a free fall problem, it's always good to write the acceleration. It kind of helps you feel a little better things. Hold on, I'm gonna take a sip of water. Okay. Hope you guys are having a nice, Sunday night. Whew. Okay, so anyway, required. What are we looking for? We're looking for initial velocity, the height, anything else? Oh, that's not so bad. Okay, so we want V naught equals question mark and delta y equals question. You should definitely know these problems. I think this is the second one of these on this. It's a different, what was the other one? The other one was the same thing, wasn't it? Small mailbag. How high does it rise? If ball's thrown vertically upwards, how high does it rise? And time, right? So time and height. Whereas down here we got V naught and height. Okay, so similar problem, so always be ready for that, okay? All right, so for initial velocity, again, you're just gonna have to get comfortable with, I guess, I don't know if I've said this yet, but you're just gonna have to get really, really, really comfortable with the equation sheet. I'm picking out these equations like it's nothing. And of course, that's because for me, I've been doing this an awfully long time. It is not a huge deal. Plus, I have the key right in front of me, right? So you're gonna have to get fairly good at doing that. So anyway, so for its initial velocity, we're gonna go, let's see, I need an equation with V naught, A, and T. So this is fairly easy. So V equals V naught plus AT. Anytime I can use that equation, I'm going for it because I love that equation because it's the easiest one to use, right? So the initial velocity will solve for that by saying V naught equals V minus AT. Okay, so I just rearranged that by subtracting AT from both sides. Okay, so V naught equals, let's see, the final velocity is 0 minus negative 9.81 meters per second squared times the time, which is 3.10 seconds. It's always nice if you have the time, okay? And sometimes you know, sometimes you can get stuck in problems and you're kind of like, I can't see a single equation that's going to do it. And if that happens, just go solve for something, right? It might make your life a lot easier, right? So anyway, so this is 3.1 times 9.81, and we end up with 30.411. So 30.411 meters per second. Notice that's positive. The negative signs cancel. And it seems to make sense, right? If we're losing 10 meters per second every second and we go for about 3 seconds, that's about how long it'll take us to stop. So this seems very reasonable. The number we would report, please don't do anything weird, computer. Okay, V naught equals 30.4 meters per second. Okay. Again, we're going to use this number if we need it in the next step. Okay, find the height that it reaches. Now, so there's two approaches here. One approach, if we're looking for height and we have time, almost always the best option is delta y equals v naught t plus 1/2 a t squared. Just because it all just plugs in nicely. It's already solved for height. But in this case, this is a calculated value, so if I can avoid using that, I probably should. So in that case, you know, I don't, you know, obviously I can plug that in here, but if I've made an error in here, then that will propagate through my, my solution. So if you want to avoid that, now obviously I'm doing the grading. You guys haven't had a lot of grading from me, but well, I don't know what was here. Meters per second squared. Okay, anyway, you haven't had a lot of grading from me, and I can usually find it if an error is being propagated through, and I try not to take off for that. But anyway, so you could do this, and you'll get the exact same answer that we're going to get the way that I'm going to solve it. But what I'm going to do is I'm going to make note of the fact that the things that I was given here work nicely in the I don't have time equation, which is v squared equals v naught squared plus, oh wait, I need v naught here too. Okay, never mind. Never mind. Anyway, yeah, so I guess either way I have to use v naught, don't I? Okay, well that's fine. Okay, so I guess there's no way around that. All right, so let's go ahead and solve for delta y. Let's use this equation. This equation is better. I use this one in the key. Okay, but let's use this one over here. So delta y, because it also doesn't mean I have to rearrange. Why did I do that on the key? I was just being a jerk, I guess. 30.411 meters per second times a time of 3.10 seconds plus 1/2 times negative 9.81 meters per second squared times the time squared 3.10 seconds squared. So delta y equals, so let's see here. Okay, let's see. My calculator says 47.137137 meters. So 3 sig figs, 47.1 meters. Okay, oh, it matches the key. So if you follow this method, you'll get the exact same answer. So either way is fine. I think I like this one better because it's already solved for delta y. Okay, it's kind of what the equation is designed for. All right. Okay, this is a doozy. I think this one showed up on a makeup. I wasn't trying to punish anybody. Maybe I was just struggling for a question. I don't really know what happened. Okay. And I'm not sure, you know, if I look at my key, I'm not sure I like it so much. So let's just start here. Okay. A tortoise can run with a speed of 0.1 meters per second, and a hare can run 20 times as fast. Okay, let's start with our, V bar tortoise. Wait, are they running constant? Yeah, they're running constant. So if they're running constant, I can put the bars on there. Not only can I put the bars on there, but I can put V naught equals V naught, right? It's all this for the tortoise, right? Like it's always the same, right? For the hare, V naught H equals VH equals V bar H equals, well, 20. So this one's 0.10 meters per second. And this one is going to be 20 times as fast. So we'll go ahead and call that, 2.00 meters per second. I guess that's one too many sig figs. Can I zoom in and like erase that extra 0? I can. Cool. All right, in a race, they both start at the same time, but the hare stops to rest for 2. That hare, man, he always does this. You think he would have learned. I really just don't think it was important to him. Okay, so here's our position versus time graph. Okay, sweet. That's what the tortoise is doing. It's not asking you to draw this picture, but I kind of recommend it. Right? When does the hare stop to rest for 2 minutes? It's interesting. I don't really like my drawing on the key. Anyway, so this is the tortoise, right? And he's going to run a distance that I'm going to call L. He runs the full length of the race, right? I think that's fairly reasonable. So the delta x for the tortoise equals a capital L. Okay. The delta x for the hare is, well, he doesn't finish the race. He loses by a shell. So he's going to go L minus the length of a shell. Right? I should note the length of a shell. What's the length of the shell? Length of a shell is 0.40 meters. Okay, so now I'm getting somewhere here. The tortoise runs, how long does he run? Well, the tortoise runs, let's say the time for the tortoise is, I don't know, let's just call it a capital T, because I don't know what that is. I know the time for the hare, well, he doesn't run as long as the tortoise, right? Because he's sleeping for 2 minutes. So we're going to say that his is the time for the tortoise minus 2 minutes, right? What do we, T nap, probably. 120 seconds. What do I want to do? Let's call that T nap. Okay, where T nap over here is, this is a really disorganized mess. Is 120 seconds. Okay, what were the sig figs on that? 2.0, so it should be just 120 seconds, not 120 point seconds. 120 seconds. Okay, so basically these are the little extra bits that we have here for plugging in. So how long does the race take? So we're looking for time. And what is the length of the race? We're looking for capital L. This is a doozy. I would probably not give this one to you guys. Okay, so the key here is these are two velocity equations. So for example, for the tortoise, and I think probably everything I just said makes sense. So the tortoise, I have an equation that looks like this. B bar tortoise equals, well, let's start for both of these. They both have the same equation to work with. Okay, V bar equals delta x over delta t. Okay, the tortoise and the hare's equations look slightly different. Okay, the tortoise's equation is based on this. So the velocity of the tortoise equals the delta x, the length of the race, divided by the time to win. Okay, for the hare, it looks like it really only takes place, so this is what the hare's line looks like. Let me see if I can get a different color here. So the hare's line looks like this. He goes really fast, and then he kind of stops. The length of a shell short, right? So this length right here, that's the length of the shell. Right? So, but for this particular part, when he's actually moving, right, the length that he moves, so velocity of the hare, he almost covers the whole thing. So his delta x is right here, L minus L shell. And how much time does he do it in? Well, T minus the time when he's napping, right? So the time when he's napping is like this time here, T nap. Okay, so now we've got two equations. And the beautiful thing about this is the only things we don't know in these equations are L and T. We know the length of the shell, we know the time of the nap. So this is just like a system of equations, okay? So solving this is work. So what I'm going to do, because I think this is going to be the easiest, I'm going to solve this one. I like to solve the easier equation and plug into the harder equation. I'm going to leave these as variables, L shell and T nap, because I just don't want to write down those numbers again and again and again. Okay, so this one's going to become L equals V tortoise times T. Boom. Okay, I'm going to plug that in over here. Say VH equals L. Oh, no, we're not writing L, are we? We're going to write, let's see, we're going to write V. Dang, I mean, I don't want red. Velocity of the tortoise times time minus L shell divided by T minus T nap. Because now we need to solve for T. That's kind of annoying, but we can do that. So we'll say VH times T minus T nap equals VTT minus L shell. Oh, son of a, okay, here we go. Let's see, VHT minus VHT nap equals VT times T minus L shell. Okay, so I want to gather these two together. So VHT minus VTT equals, I'm going to bring this one over to the other side, VHT nap minus L shell. Okay, we're going to pull the T out from this side, so we pull the T out. I'm left with VH minus VT equals, we can leave all that alone, VHT nap minus L shell. So T equals VHT nap minus L shell divided by VH minus VT. Okay, at this point, I should be ready to plug in. So the time is, let's see, VH, the hair was going at 2.0 meters per second. The time of the nap was 120 seconds. The length of the shell was 40 centimeters. Oh no, that's rough. That's sig fig wise, that's just a 0.4 meters. That stinks. Okay, and then we're going to divide that by VH, which was 2.0 meters per second, minus VT, which is 0.1 meters per second. Okay, if we check the units here, we'll note that these two multiplied times each other give meters. This is a meter, so we have meters on top. And we're being divided by meters per second, so we're going to end up with seconds. Okay, so T equals 126.10 seconds. Okay, so just a hair longer, or just a midge longer than the nap. Unfortunately, from sig figs, this is a terrible question, right? So from sig fig standpoint, we've got one sig fig here, we've got one here. So let's see. So technically, we've got one decimal place on the bottom. So this is 1.9 on the bottom. On the top, we're going to have, what was that? 2 times 120. It was 240. Right, so the 4 is significant. Minus 0.4. So basically, we've got no decimal places on the top. Well, really, we've got 2 sig figs on the top divided by 2. So we should have 2 sig figs in this. So I guess with 2 sig figs, this would be 130 seconds. I hate significant figures, right? But anyway, this is the one we're going to work with. So if I want to know the length of the race, I'm going to go up here and I'm going to choose whichever one of these I think is easier. I'm going to choose this one. That's the easiest one for getting the length. So the length of the race is velocity of the tortoise, 0.1 meters per second, times the time I just solved for, which was that 126.10 seconds. 126.10 seconds. So the length of the race is 12.610 meters, excuse me. And let's see, so this technically should have had how many? We decided 2 sig figs, but that clearly has 1 sig fig. So we're going to have 1 in this answer, so 10 meters. That's a really awful answer. I got to do a better job of giving people reasonable answers with sig figs. It looks like last year I decided not to bother with this because that 40 centimeters. Oh, it's 0.10 meters. Okay. All right, never mind. That takes some of the pressure off. Okay, so it should be 13 meters. Okay, so this last problem here, if you didn't like it, if it, gave you heartburn, this is almost certainly an honors question. I don't know how it snuck onto this particular test. Maybe I had to make an adjustment for somebody. But anyway, so there it is. So if we zoom all the way out, you can see all of our work that we've done over the past hour. All All right. I hope that's helpful. Y'all have a good one. And always remember, take a breath. Remember, there's a lot of things a lot more important in this class. So take care of those things. And obviously, as always, if I can help you, please let me know. That's what I'm here for. Take it easy. Bye.